Sort. How does this one work?
Insertion sort uses a different strategy. It builds the final sorted array one item at a time.
One item at a time.
Imagine you have a hand of cards you're trying to sort. You pick up one card at a time from the deck, the unsorted part, and you insert it into the correct position within the cards you're already holding, the sorted part.
Okay, I like the card analogy. So you maintain a sorted sublist.
Exactly. You start by assuming the very first element is a sorted sublist of size 1.
Trivial case.
Right. Then you take the second element, you compare it with the first element. If it's smaller, you shift the first element over and insert the second element before it. Now your sorted sublist has 2 elements.
Okay, so the sorted part grows from the left. Let's use the notes example.
Yeah.
36, 24, 10, 6, 12.
Perfect. Start with 36. Sorted sublist is just 36.
Next is 24.
Compare 24 with 36. 24 is smaller. Shift 36 right. Insert 24, sorted sublist. 24, 36.
Next is 10.
Okay, take 10. Compare with 36. 10 is smaller. Shift 36. Compare 10 with 24. 10 is smaller. Shift 24, we're at the beginning. Insert 10, sorted sublist. 10, 24, 36.
I see. You compare backwards through the sorted part, shifting elements until you find the right spot.
Exactly that. You find where the new element fits and make space for it by shifting the larger sorted elements one position to the right.
The notes have another, more detailed example
Mm-hmm.
with 67, 33, 21, 84, 49, 50, 75. It really shows that shifting process clearly.
Yes, that walkthrough is good because it shows elements like 84 being inserted later without much shifting, while smaller elements like 21 cause more shifts as they move towards the beginning of the sorted sublist.
Let's look at the pseudocode for insertion sort.
Okay. It takes the array A of n numbers. The outer loop I starts from 1, not 0, because A0 is our initial sorted list. It goes up to n1.
Right, iterating through the unsorted part.
Inside, it stores the current element AI in a temporary variable. Let's call it swap again, or maybe key is better here. It also sets a position marker, pose, to I1, pointing to the last element of the sorted sublist.
Okay, key is the element we're inserting. Post points into the sorted part.
Now, a while loop kicks in. It checks 2 things. Is pose still within the bounds of the array? Pose is 0. AND is the element at a pose greater than our key.
So while we're still in the sorted part and the element there is bigger than the one we're trying to insert.
We shift APOS 1 position to the right into APOS plus 1. Then we decrement POS to look at the next element to the left in the sorted sublist.
Shape shifting until one of those conditions is false.
Right. Either we find an element APOS that is not greater than our key, or we fall off the beginning of the array. POS becomes -1.
And
Then the while loop stops, and the correct position for our key is at POS plus 1. So we place key into APOS plus 1.
into the empty slot created by the last shift or at the very beginning.
Exactly.
The C++ code snippet and the walkthrough with our 23, 1, 10, 5, 2 make this very concrete. You can see the sorted version growing.
Yes. Combining the pseudocode, the C++ code, and a visual example usually helps solidify how it operates.
Let's talk efficiency. Time and space complexity for insertion sort.
Okay, time complexity, best case, the list is already sorted.
What happens then?
Well, for each element, the while loop condition is APOS key, is immediately false. So you do minimal work for each element, that's ON time, linear. Very good.
Nice. But what about average or worst case, like a reverse sorted list?
That's the worst case. For each element you insert, you potentially have to compare it with and shift all the elements already in the sorted sublist.
So the inner loop runs many times.
Yeah. That leads to ON2 complexity for both average and worst cases, similar to bubble sort in that regard.
In space complexity, how much extra memory?
That's one of its strengths. It's O1, constant space. It sorts in place, meaning it rearranges the elements within the original array, only needing a tiny bit of extra space for temporary variables like key and pose.
So summing up insertion sort. Advantages, disadvantages.
Advantages, simple to implement. It's stable, which means elements with equal values maintain their relative order.
Oh, that could be important sometimes.
Yes, it's efficient for small lists. Very efficient for lists that are already mostly sorted, that ON, best case. It uses minimal extra memory, O1 space, and it's adaptive. It gets faster if the input is partially sorted.
Disadvantages.
The main one is that ON2 average and worst case time complexity. It just doesn't scale well for large, randomly ordered lists compared to other algorithms.
Where does it get used then, given that limitation?
It's great for those small lists or nearly sorted list scenarios. Your notes also mention it's often used as a component within more advanced sorting algorithms.
Like a helper.
Exactly. Algorithms like TimSort, used in Python and Java, or IntroSort might use something like QuickSort or MergeSort for the big picture, but when the subproblems become small enough, they switch over to Insertion Sort because it's faster for those small sizes.
Ah, a hybrid approach, using the best tool for the current scale.
Precisely. It's also used in bucket sort sometimes.
Okay, that makes a lot of sense.
Okay.
Let's move to the third